Welcome to Immunoassays and Aptamers. So, fluorescence is often used in immunoassays. Now, immunoassays use antibodies to detect our analyte. And remember that an analyte is a protein produced by the immune system in response to an antigen, which is a foreign molecule. The antibody binds to the antigen, but not to other molecules, at least ideally. That is, the antigen-antibody formation constant is very large. So here's an example immunoassay, where antibody 1 is bound to a polymer support. So up here, we've got our antibody. This is the Y-shaped blue molecule up here. That's bound to our gray polymer support. Then antibody 1 is exposed to our sample. In here, we have our analyte molecules bound here and there. The analyte binds to antibody 1. Now naturally, the antibody must be chosen so that it binds to the analyte of interest. The fraction of antibody sites that are occupied by the analyte is then proportional to the analyte concentration. Our excess sample is washed away, and our surface is then exposed to antibody 2, which binds to a different portion of the analyte. And so that's what we have occurring down here. We have antibody 2, that's this grayish molecule there, that's binding to a different portion of our analyte, the top in this case. Now, note here that antibody 2 was previously modified such that a specific enzyme was bound to it. So we have our antibody 2 there. We've got this other enzyme here that's bound to our antibody 2. Now note that in the center here, where we didn't have any analyte bound, we don't have any of our antibody 2 or enzyme bound there either. Next, excess reagent is washed away, and the enzyme is now used in one of two ways. Either the surface is exposed to a colorless reagent that the enzyme converts to a colored product, or the surface is exposed to a non-fluorescent reagent that the enzyme converts into a fluorescent product. And then the absorbance or fluorescence is monitored, and because a single enzyme can catalyze the production of many absorbing or fluorescing product molecules, then the chemical signal is amplified. Now, we've amplified the signal not electronically, but chemically. We're using these enzymes to many times create our product molecules that are either absorbing or fluorescing. And so now, for each analyte molecule that we now have a lot more of our absorbing or fluorescing molecule. So such immunoassays can be sensitive to under a nanogram of analyte. For example, pregnancy tests, which I've shown here, use an immunoassay to detect a placental protein in urine. And these are really quite sensitive because we're using that enzyme to catalyze a large number of reactions that then produce our colored product. And so you see here that going from one to the next, we get darker and darker line there indicating a positive test result. There actually is a slight positive result there on this first one. So advantages of immunoassays include that they can be performed in the field. They can be performed quickly. This is around 20 minutes to a few hours. They require relatively small sample volumes. 1 milliliter or so is generally enough. Whereas in contrast, chromatography must be done in a lab after the analyte is extracted or concentrated from somewhere around 1 liter volume quantities, which generally takes a few days. And the sensitivity of a fluorescence immunoassay can be increased 100-fold using europium-3+ and time-resolved luminescence measurements. Because organic fluorescent molecules like fluorescein are useful, but the background fluorescence from solvent, solutes, and particles can limit their utility. The background fluorescence decays to negligible levels after about 100 microseconds. So we have our initial pulse of light coming in. This is a laser pulse generally. We then have some background fluorescence that decays rather quickly. And then what we want is some long lifetime of our fluorescence so that we can monitor after that background fluorescence has passed. We can monitor in this range what the signal is of our europium-3+. So if we have some fluorophore that decays over a longer time frame, we can then ignore the signal from the first 100 microseconds or so after the excitation light pulse from a laser, and this means that our background fluorescence is largely gone. And our europium 3 plus displays this sort of fluorescence at 615 nanometers. The fluorescence decays to 1 over E, so this is 37% of its original intensity in around 700 microseconds. So now let's turn to aptamers. An aptamer is a piece of DNA or RNA with somewhere around 15 to 40 base pairs that strongly and selectively binds with the analyte. The aptamer is chosen by exposing the analyte to a pool of random DNA or RNA sequences, then washing away any unbound sequences, replicating the bound nucleic acid sequences, and repeating this procedure over and over again. Now, once our nucleic acid sequence is known, then the aptamer can be synthesized in large quantities. Now, the aptamer behaves just as an antibody would in an immunoassay, so we can use it just like we would an antibody. It's essentially just an artificial antibody that we've made in the lab. And that was Immunoassays and Aptamers.